Hi and welcome to the presentation of path planning. I am Varun Raghunathan and I will now explain the project that I did for my coursework on image processing. Our objective here is to develop and implement path planning for a robot to traverse an indoor environment. To do this, we will use MATLAB. We'll get back to that later, but first, let's see what path planning is and how exactly we try to do it in real time. That's the problem statement. The scope of this project can be further extended by programming the robots for their applications in an appropriate situation. It can be for solving by Mars rovers sent to space and many more. The basic requirement for the path planning are as follows. First, the vision system. It records the position of the robot, the destination, and the obstacles. And next, the strategy system. It decides where the robot should move and how the robot should move. And next comes the communication system. It is responsible for the proper communication between the computer and the robot. And then, finally, the onboard processor. This receives the command and drives the robot based on the result of execution. But our focus is just on the vision and mainly on the strategy system. And this is how a typical indoor setup will look like. You have the camera as the vision system, your computer, that's the strategy system, and the onboard processor decodes the path planned and sent by the strategy system and drives the robot. And here you have the flowchart. Now, the algorithm that we are going to use is called A-star algorithm. A-star is one of the many search algorithms that takes an input, evaluates a number of possible paths and returns a solution. If there is a solution, A-star will find it, which makes this search algorithm complete. Similar to the greedy best first search, but is more accurate because A-star takes into account the nodes and that have already been traversed. And this is an example of how the terrain would look like with an overhead view. You have the starting position and the destination is here. The traversable path is around this and the obstacle. You have all this color coded. So the vision system captures this image and gives it to the strategy system, like an overhead camera taking a picture of the arena and sends the picture to the computer. The computer forms a gridded image from the original image, so something similar to this one. So basically, the robot can move in 8 directions, that is, horizontally 2 ways, and vertically 2 ways, and diagonally 4 ways. Let's say we define cost to each movement. Horizontal vertical take a cost of 10 and while the diagonal costs 14. Now this algorithm uses the formula f of x equal to g of x plus h of x. Now what is g of x? G of x is the total distance from the initial position to the current position. That is, from, let's say this is the initial position and we have to move to some point, say to this one. So g of x would be the distance from here to here, and h of x is the heuristic function that is used to approximate the distance from the current location to the goal. So let's say this is the starting node, this is the destination, and let's say you're somewhere around here. So the thing is, you have some value for g of x which is from here to here, and the h of x that we need to calculate for this node would be from here to here, and this is just an approximation. So what approximation we use is just we use vertical or horizontal transpose. So for this, say we traverse from here to like this and then here, so 1 hop, 2 hop, 3 hop, and from here 1 2. So this would be the approximation of h of x. Then we have, so f of x equal to g of x plus h of x. This is the current approximation of the shortest path to the goal. Then you have this. When starting at the initial node, the search keeps track of the nodes that's to be traversed. This is known as the open set, and it keeps track of the nodes in order of the lowest f of x to the highest f of x. In order of priority, each node is removed from this queue, and then the values for g of x and h of x Neighboring nodes around the removed node are updated. This search continues until it reaches the node with the lowest f of x value, which is called the goal node. So h of x at the goal node is 0, which is an admissible heuristic because the path to the goal is clearly not an overestimate. So at the start you have such an arrangement. Of all this particular node promises the shortest path to the destination. So from here we hop to this node. This is because f of x value for this particular node is the lowest of all the other nodes. Say this is 40 and all the others seems to be more than this one. So we hop to this node. Then the first path is highlighted in purple. The only option is the purple with f of x equal to 40 because A star will choose the path with lowest f of x only, as I said before. And then this is how we compare with the other things. So now you see that once you hop to this node, you update the nodes around this, that is that you update the neighboring nodes around this node to match the value with this one. So say first the values were, these nodes were 54, 60, 54 and 60. But now once you go to this node, so these node became to neighbor to this one. So the value becomes f is equal to 60, 74, 60 and 74. You get the math. So you updating the weights according to the newly visited block, we write the final weights comparing with the previous one. So you just compare these values with the previous values, that is you compare 60 with 54, 74 with 60, 74 with 60 and 60 with 54, and you only update it when this new value is less than the old one. So I don't think anything is new, any new value is lower than the new old one, so we just exclude those things. Similarly we just continue our traversal. So once you have gone to this node, you include this to the visited nodes. So the other nodes that is not visited are these, and among these only this particular node is having the lowest value. So you go to this node, and the neighboring nodes to these is highlighted with the black thing. So these are the nodes that get updated with this node. So following the same thing, you just get something like this, until you reach the destination. This arrow mark indicates from where you have hopped to this particular node. So let's say for this particular arrow means that you have hopped from this node to this node, similarly to the all. So once you reach this destination node, what you do is you just backtrace using this arrow. So this would be your destination. So when you backtrace it from here, this arrow points to this. So when I backtrace, this arrow goes to here. So when I backtrace this, it goes here and here and here and here. So thus we have our path like this one. So this is our path. So this backtracking thing is an optional thing, so you could use however you want. And that's the algorithm for you. And this is a simulation for path planning. Here you can see all these blue things or the obstacles, and I have the robot here and here, and these are the target. So once I input this image to MATLAB, and this is the planned path I get from the MATLAB. So you could see the path. This robot is planned to this target, and this robot is planned to this target. And you can see here that for this robot too, there is no path to the target because it is totally blocked. So in such cases, you can notice we have no path exists. The algorithm does so. It finds there is no path, and if there is a path, this algorithm will find it for definitely. It might not be the shortest path sometimes, but for all the trials that I did, it was the shortest path. So you could have the example here too, and this is the exact image that I gave for my project. This is the result that I got. See, you could see the path planned. This is the robot, this is the destination, and these are the obstacles, and this is the traversable path. And this is the gridded image of the same thing, and something similar to the one which has no path. See, it is totally barred from this robot, so it has no path, and so obviously you can't find the path. But whereas for this one you have a path, so it plans for it. You get the gist. and I have listed some future applications and applications that this algorithm can be used currently. And that ends with the presentation. Now let's see the MATLAB code. Just a second. Sorry for that. And this is my main starting program. So have given this sample image as the input image. As I don't have a camera, I'm just giving a direct image as an input. So let me run. See, you were able to see this small dot go and trace the path. So that is the path planning for you. And the time taken to complete path planning is 0.6922 seconds and 5.670. That is for the two things. So repeat the same for sample 3. So you see there's no path for this to this, and you were able to see the path traced by here. So that's path planning for you. Then for the real-time implementation, as part of an experiment, you can use the following. First, you see this is an Arduino board, and this can be used as the onboard processor so that you could drive your robot. And for the robot, you can use an omnidirectional robot that would be in handy with this project. Let me show you a video of that. So this is how an omnidirectional robot would look like. So you see you have the four wheels which are orthogonal to each other, and it can move in all directions. It doesn't need to turn around. It can move in all directions, that is the 8 directions, without turning. You can see how it functions. So this is very easy to do. It just needs this omnidirectional wheels, that's all. So that's the robot for you. Now let me show you one real-time implementation of this path planning.
A new system could help robots navigate through crowds in the same way people do. Here, a virtual robot is placed in a simulated crowd. An algorithm trains the robot to get through the oncoming crowd by continually modifying its route. In another scenario, the robot joins the natural flow of the crowd. Although it doesn't take the most direct path, it's a more socially acceptable way to get from one end to the other. The technology could help robots integrate better into society.
And that's path planning for you. Thank you for watching my video and have a great day.